Okay, so in the last video I did, we talked about electron configurations and the normal predicted configuration for elements on the periodic table. And while that will cover the vast majority of your elements, there are some elements that are exceptions to normal configurations. And so when you encounter them, they don't necessarily exactly follow Aufbau's rule. They will still follow Pauli's exclusion principle. They will still follow Hund's rule, but it gets a little dicey with the Aufbau. So according to Aufbau, we fill the lowest energy level available completely before we move to a higher level. In these exceptions, we actually see that some of the electrons are moved from a higher level to a lower energy level, but not necessarily in the sequence that we would ordinarily fill them. So that's what I'm going to show you are those exceptions. So we're going to encounter this in the D subblock. You're also going to see it in F, though I'm not going to hold you responsible for the F ones, only the ones in D. And we're going to see them in the D4 elements and the D9 elements. So the D4 elements, when I say the D4, I mean, here is my D block, 1, 2, 3, 4 over chromium, molybdenum, tungsten, and seborgium. So we're going to see that those ones will actually steal an electron from their outermost energy level, which will be an S, and they will move it to the previous D block to make that D block a half full subshell, which then results in a larger number of unpaired electrons. We also see the same thing in our D9 elements becoming D10. So that would be copper, silver, gold. And we're going to ignore this one down here. Sorry. I should move that so you could see it. The copper, the silver, the gold. And we're going to ignore this one down here. I'm never going to ask you about it. So just those three. So Cu, Ag, and Au. All right. So this actually makes a little bit more sense when I draw one out. So we're going to draw one out for, I'll do chromium and copper, just because those ones are the easiest two to do. So for chromium, 24 electrons. So I'm going to do what you would expect to see in black, and then I'll show you what you'll actually see in the pink pen. So according to Aufbau, this is what we would see for chromium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And then I'm going to take these two and I'm going to write out their orbital diagram just so I can show you what you would see. So 4s, 1 up, 1 down, 2, 3, 4, 5, 3d, 1, 2, 3, 4. So this is what we would expect, right? But what we actually see, the way this occurs naturally, wow, I can't spell. There we go. What we actually see is that the 4s, which is our outermost energy level, gives up one of those electrons that it has to the 3d, so that 3d will then be half full. And so because this is on the outside, the outermost energy level, but it fills first, which is why it's full, and the 3d, which fills after but is actually below it, fills second. So what I would see when I wrote this out would be this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. And so then when I draw the orbital diagram out, we'd have 4s1, 3d, 1, 2, 3, 4, 5. So how many unpaired electrons do we have in the expected? We would see 4. How many unpaired electrons do we have in the actual? We would see 6, right? These 5 and that 1. And so this is what chromium actually does. And then the same thing with molybdenum, tungsten, and seborgium, right? Whatever the outermost S is, right? 5s, 6s, 7s, They pop one off from that, and then they put it in that D, whatever D4 that is missing one to make it a D5. Okay, and so you just have to know anytime you encounter those 4 elements, it's not this, it's actually this. Okay, the expectation is that you know that. All right, let's do copper. So we can show a D9 to a D10 one. So copper has 29 electrons. So same thing, I'll do the expect in the black. I would expect this 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. And then for the orbital diagram, if I just show the last part, because we know that all this part is full, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 unpaired electron. Then if I do the actual, it looks like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Now, what's interesting about these particular ones is when I do the 4s1, 3d10, I still only have 1 unpaired electron. It's just a different unpaired electron. It's an outer electron. Well, that outer electron, as we'll find out later, is going to be easier to steal away so that we can start to make some ions. Metals make positive ions, so when we start taking those electrons off, we start to get those positive ions. Okay, so again, you need to know anytime you encounter something in a D4, it's going to be rearranged to make a D5 by stealing from the S and moving. Anytime you encounter a D9, it's going to be a D10 for the same reason, stealing from the S and moving. Those are exceptions to expected configuration. You need to commit to memory, and anytime you see one, whether it's on homework or quiz or test, you need to make sure that you respect that exception and you draw it that way.